Hey Robin, what's the difference between a soda can and a loaf of bread?
Hey Jacqueline. That sounds like the setup for a joke, but actually, it's a pretty interesting material science question. Hi, I'm Robin. This is Kitchen Matters. We are a team of material science grad students helping you to understand the science of your kitchen. Today, we're going to talk about polymers, the twisty, windy macromolecules that give everyday objects like plastic, adhesives, and even foods some of their most amazing materials properties. If you look at the word polymer, you see two roots, the word poly, meaning many, and the word meros, meaning part. Put them together and you have a polymer, a long molecular chain comprised of many repeating parts. These repeating parts string together to make one long molecular chain, and these chains get all tangled up together to form something that's actually pretty unique. You see, metals and glasses form networked structures where all of the individual atoms are bonding to multiple partners, like this. In contrast, polymers look much more like this, a tangled, seething mess of spaghetti. And in general, that structure gives you a set of materials that are soft, flexible, and stretchy compared to metals or glasses. If you start to look around your kitchen, you'll begin to understand why we care about polymers. Think about the way that some cheeses stretch, but others crumble, or the way that potato chips crunch, but butter spreads. Of course, there's more in food than just polymers, but polymers are one of the things that gives food its incredible array of physical properties. Today, we're going to be talking about that, about the way that polymer structure and processing are connected to behavior. And in particular, we're going to talk about the effects of chain length, flexibility, and intermolecular forces. First, let's think about what happens when we change the length of polymers. Here, I have two identical piles of noodles. I just cooked both of them. They're the same length. And all I'm going to do is take one of them and tear it up a couple of times. Okay? And I'm going to mix it all together, hopefully get it all tangled up again. And I'm not going to do anything to the other pile. I'm just going to tangle it up again so that we make sure that the tangling didn't have some impact on our experiment. Now, formulate a hypothesis. Which of these two piles do you think is going to be easier to pull apart? Well, there's only one way to find out. Let's do an experiment. First, I'll pull apart the noodles of the original length. And that goes, but it takes some effort. You see, I had to tear through multiple noodles for that to work. Here, we'll try the small ones. And this was a lot easier to pull apart. There were fewer noodles that I had to break. In an extreme case, you can imagine making the noodles really small. And here, it takes almost no effort to pull this pile apart. Just to tie things up, the length of a chain is connected to its molecular structure, and that, in turn, affects the properties and the performance of ingredients that we use in our kitchen. But it's not the only way to change things. Another thing you could do is make chains more rigid. And to think about that, we're going to consider what would happen if we froze the spaghetti. So here we have two piles of spaghetti. We have a brittle one, which we took just out of the freezer, and we have a fresh one. And what you'll see is that there's a big difference here in terms of how easy it is to pull things apart. I can pull that apart quite easily, but if I pick up a single strand here, it lifts the whole object. When our molecules are more rigid, it's harder to disentangle them, and that in turn makes the polymer stronger but brittle. Think about butter. At low temperatures, butter is actually pretty strong and rigid. But as you heat it up, it becomes a lot more spreadable and flexible. And that is because the polymers in the butter are becoming less rigid, making it easier for them to slide past one another. Finally, like spaghetti, polymer chains have these sort of sticky interactions that make them want to stick together. And this has a pretty big effect on polymer properties too. And basically you can see this in the spaghetti because you see that there's something sticking these two molecules together. And that appears on a molecular scale too. So you have intermolecular forces that form between strands of polymers. And that helps hold this whole mess together. So, with our spaghetti, what do you think will happen if we add vegetable oil to help dissolve these molecular interactions? Well, let's try it. I'm just going to throw this polymer into a bowl, and I'm going to add a healthy serving of vegetable oil. So, I mix this all together. Once it's mixed, you'll see that I can just pull it apart, one strand at a time. That is very different from this, where if I try to pull it apart one strand at a time, I'll yank the whole thing apart. This has been Kitchen Matters. Thank you all so much for watching, and hopefully you now understand why they don't make bread out of soda cans.